Hello, welcome to another module in this massive open online course. So, we are looking at convex functions. Let us continue our discussion. So, we want to continue our discussion on convex functions. Okay. And well, now let us look at a test for convexity. Let us consider first function of a single variable x, y equals f of x. This is a scalar variable. We will consider, we will come to functions of vectors later. So, this is a scalar variable, and well, this is convex if d square y by dx square equals d square f of x by dx square, that is the second derivative is greater than or equal to 0. And remember, this is for a function of a scalar, that is a function of a one dimensional variable x, of a single dimensional variable, a single variable x. Alright. So, if the second derivative is greater than or equal to 0, then the function is convex. Okay. And this can be understood as follows. For instance, if you plot a convex function, now what you will see is, if you look at the derivative of the function at different points, okay, if you look at the derivative, which is nothing but the slope, okay, derivative, okay, is slope. So, this is your x and this is your f of x, and if you can look at the slope of the function, right, which is given by the slope of the the derivative of the function, which is given by the slope of the tangent at each point, you can see that the slope of the tangent or the derivative is increasing for a convex function. Always slope of tangent equals dfx by dx is increasing, which means we know the test for an increasing function is if its derivative is greater, that is the derivative is increasing. Alright. So, if function is increasing if its derivative is greater than or equal to 0, alright, a function is monotonically increasing if its derivative is greater than or equal to 0. Now, here the slope is constantly increasing, monotonically increasing, which means that the derivative of the slope must be greater than or equal to 0, which implies, since the slope is constantly increasing, this implies that the derivative of the slope d by dx of dfx by dx must be greater than or equal to 0 for a convex function, and which gives us the result that d square f of x by dx square greater than or equal to 0. This is basically nothing but the condition that the slope or the derivative is constantly increasing. Slope of tangent is monotonically increasing for a convex function. is monotonically increasing for a convex function. Okay. Let us take an example. Consider f of x equals e raised to the power of ax. Okay, for any a can be less than 0 or equal to 0 or greater than 0, then dfx by dx equals d over dx of e raised to ax. This we know the derivative of the exponential, this is a e raised to ax. Now, if you take the second derivative, d square fx by dx equals d square or derivative of the derivative, that is d over dx of a e raised to ax, which is a square e raised to ax. Now, we know e raised to ax, the exponential, this is always greater than, in fact this is always greater than 0. A square is greater than or equal to 0 implies this is greater than or equal to a square e raised to ax is greater than or equal to 0, alright, because a square is always non-negative, alright, a square is always greater than or equal to 0. So, this implies for any value of a, d square fx by dx square is greater than or equal to 0 implies e power ax equals convex, and it is always convex irrespective of a can be either negative, if it is negative it is a decreasing exponential, if it is positive it is an increasing exponential, and both are convex. So, e raised to ax is always convex, and the derivative test, that is the second order derivative, also confirms that. Okay. All right. Let us look at another function that we have seen yesterday, that is f of x equals x square. You can recall that it is given something like this, correct. This is f of x equal to your x, and this is your x square, and you can see that if you take, this is very straightforward, dfx by dx equals 2x, and d square fx by dx square equals 2, which is greater than 0, implies x square equals convex. Okay, x square is a convex function. On the other hand, if you take f of x equal to x cube, you will notice that d of x over dx equals 3x square, and d square f of x over dx square, second order derivative is 6x, is greater than 0, greater than is equal to 0 only if x is greater than equal to 0. Now, this is greater than equal to 0 for x greater than equal to 0, implies x cube is convex only if only for x greater than equal to 0, and in fact that is what we had seen in the previous module. If you plot x cube, just to refresh your memory, it looks something like this. All right, so this part is convex, and less than 0 it is concave. Okay. All right. Now, how about concave functions? Let us look at, we have to test for the convexity of the negative of that function, correct. So, let us consider again our classic examples for concave functions, that is the natural logarithm of x. Now, minus f of x equals minus ln of x. So, to show first differentiate minus the natural logarithm of x, this is minus 1 over x. We are considering minus of x, since to demonstrate concavity we have to demonstrate the convexity of minus of f of x. Okay. Now take the second derivative, d square over dx square of minus ln of x equals 1 over x square, which is greater than equal to 0, implies minus ln x, minus ln x equals convex, what we had seen in the previous module, implies ln x equals the natural logarithm of x is concave. Okay. Again square root of x, f of x equals square root of x, minus f of x equals minus square root of x, dfx by dx equals, well, dfx by dx equals well, this is minus 1 over twice square root of x and d square fx by dx square, this is equal to 1 over 4 x to the power of 3 by 2, which is greater than 0, implies, well, minus square root of x equals convex, implies square root of x equals concave. Okay. And that is what we had seen yesterday. If you plot square root of x, it looks like this, and this is concave. Okay, and this is concave. Okay, so this is square root of x. All right. Let us now come to the norm. Again, norm you cannot use the second derivative test. Let us look at another interesting function. In fact, let us look at a practical application of this. This is an interesting aspect, and we have also seen this before. So, let us come to an application. Let us look at y of x let us look at f of x equals qx, where qx is the Gaussian Q function. Okay. The Gaussian Q function, remember, this is the CCDF, complementary cumulative distribution function of the standard normal random variable. There is a Gaussian random variable with mean 0 and variance 1. This is also the tail probability of the standard Gaussian random variable. Okay. You can recall this is given as follows. If you have a PDF of the standard normal random variable, mean equals 0, variance equals 1. This is the CCDF, that is the probability that x is greater than or equal to x. Okay, so this is the tail probability. This is the tail probability. Okay. Also the CCDF. Okay, the complementary cumulative distribution function, which is basically the probability that x is greater than or equal to x. This is your qx, where x equals standard normal random variable. Denoted by n of 0 1, that is Gaussian random variable, mean equal to 0, variance equal to 1. Gaussian random variable with mean equal to 0 and variance equal to unity. That is basically the CCD of that random variable, the complementary cumulative distribution function of that random variable is basically the Q function. And remember, the expression for the Q function, we have also seen that, or you must also be familiar with that, that is basically 1 over square root of 2 pi integral of the Gaussian probability density function, or let me write it, integral of x to infinity, since it is the probability that it is greater than or equal to x, integral of x to infinity e power minus x square by 2 dx, which if you take the constant outside, you can also write this as integral x to infinity e raised to x square, I am sorry, e raised to, you can use a different variable of integration, e raised to minus t square by 2 dt. Okay. Now, this Q function is a very interesting, and it frequently arises in communication and signal processing also, because this Q function represents the bit error rate. You might have seen the expression Q of Q of square root of 2 EB over N naught, which you can also write as Q of under root of SNR or 2 times SNR, depending on how you define it. So, this denotes the bit error rate. This is the bit error rate of the wireless, the bit error rate of a additive white Gaussian noise channel, BPSK, bit error rate of BPSK, binary phase shift keying over an additive white Gaussian noise channel. This is the bit error rate over an AWGN channel, and in fact, it has a lot of applications. It arises quite frequently, as I said, in communications as well as signal processing. All right. So, now what we want to show is that this Q function, which has a lot of practical applications, that this is convex. We want to demonstrate that this is convex, and in fact, that is convex for x greater than or equal to 0. This is a slight qualification, it is not convex over the entire x, convex only for x greater than or equal to 0. In fact, we start with the definition Q of x equals, well, 1 over square root of 2 pi integral x to infinity e raised to minus x square by 2 dx. You take e raised to minus t square by 2 dt. I apologize. We form the first derivative of this, that is 1 over square root of 2 pi, derivative of the top limit, which is 0 because of the constant, minus the derivative of the bottom limit, correct. So, we have minus derivative of the bottom limit is derivative of x, which is 1, times the integrand evaluated at the bottom limit, that is e raised to minus x square by 2, that is it. So, the derivative of Q of x is minus 1 over square root of 2 pi e raised to minus x square over 2. Now, which means if you take the second derivative of this d square q x by dx square, that will be minus square root of 1 over minus 1 over square root of 2 pi minus 2x over 2 e raised to minus x square over 2, which is equal to, if you look at this, which is equal to x over square root of 2 pi e raised to minus x square by 2. And now you can see, now this is always greater than or equal to 0, e raised to minus x square by 2, x is of course greater than or equal to 0. So, when x is greater than equal to 0, this is greater than equal to 0, which means greater than equal to 0 if x is greater than equal to 0. So, we have the second derivative d square qx by dx square greater than equal to 0 if x greater than equal to 0 implies that the q function q of x is convex if x is greater than or equal to 0, and this is in fact a very interesting property that will again use in fact quite some time in the future. If you look at a plot of the q function, that is a CCDF, it is decreasing constantly. At 0 we have q of 0 equals half, because this is a CCDF, the probability that x is greater than 0 is the point of symmetry, correct. Q of 0 is a probability that x is greater than equal to 0, which is half, which is equal to the probability that the random variable x is less than equal to 0 for this standard Gaussian random variable with mean 0 and variance 1. Okay. So, q of 0 equals half equals probability x greater than equal to 0, q of infinity equals probability x greater than equal to infinity equals 0. So, at infinity it is 0, q of minus infinity equals probability x greater than equal to minus infinity, since it has to be greater than equal to minus infinity, I am sorry, x has greater than equal to greater than, in fact we can just replace this by greater than equal to, greater than equal to, greater than equal, does not matter. Okay. So, this is x greater than minus infinity is 1, therefore, it starts at 1 and it decreases, and therefore, if you look at this portion, this is convex, okay, and this is half at x equal to 0, this is half, q of x is half, this is convex, and this is this portion which is less than 0, this is concave. Okay. So, this is your q function, it is convex for x greater. So, q function is basically convex for x greater than or equal to 0. Okay. So, that is what we have seen. All right. And finally, coming now to the norm it is straightforward to show that it is convex. The two norms. So, well, first we note the triangle. So, first consider the norm. Now, what we want to do is we want to consider any two vectors x1 bar, x2 bar. We want to find the norm of theta x1 bar plus 1 minus theta x2 bar, okay, the norm or the value of the function at the convex combination. Now, using triangle inequality, we know that this is less than, now observe that of course, for any convex combination 0 is less than equal to theta less than equal to 1. So, this is norm of theta x less than equal to norm theta x1 bar from the triangle inequality. Okay. We are using the property here that norm a bar plus b bar is less than equal to norm a bar plus norm b bar. Now, theta and 1 minus theta are greater than equal to 0, because 0 less than equal to theta less than equal to 1. So, this is simply norm of theta times x1 bar is theta times norm of x1 bar plus 1 minus theta norm of x2 bar, which is basically your theta times f of x1 bar plus 1 minus theta times f of x2 bar, where we have f of x bar equals norm of x bar, the two norm. Okay. So, all these are basically the two norm, and this is your f of theta x1 bar plus 1 minus theta times x2 bar. So, what we have shown is f of theta times x1 bar plus 1 minus theta times x2 bar is less than or equal to theta times f of x1 bar plus 1 minus theta times f of x2 bar, implies f of x bar equals norm, the 2 norm, this is convex. Okay. So, this is sort of a straightforward way to show that the 2 norm is convex, the L2 norm is convex. However, this might be a slightly cumbersome way to show it, especially for any function of a vector, correct, or a function of more than one variables, that is the function of a vector. All right. So, one has to devise a general test to demonstrate, similar to the test that we have shown earlier, the second order derivative test for a scalar, for a function of a scalar variable, single variable x, one has to derive, or one has to arrive at a similar test for a function of a vector, all right, which is something that we are going to develop or look at in the subsequent modules.